Okay, so today's session is entitled How Bad Can Things Really Be Given Zero Observed Defects? And what I'm going to introduce here is kind of a risk tool or a rule of thumb, which kind of will help you understand what a risk level could be given that you find zero observed events in, let's say, a sample. So I'm going to talk mostly from the quality aspect or arena here, but this is certainly applicable in many, many different types of areas. So you can imagine, let's say, a supplier who's got a bunch of, let's say, product on hold, and they've sampled some product and they found, let's say, zero, non-conformances, and they always come back and say, well, I found, nothing in the sample, so therefore the rest of the product must be, defect-free. The fact of the matter is, depending on the sample size and depending on the actual, potentially inherent defect rate, you simply may not find any events given those factors. So this is where this 3 over n rule comes in, and it basically gives an upper level risk given that you've found zero events or zero, let's say, non-conformances. So here P is the upper level risk value, and n will be the sample size. The 3 is just part of the derivation of the formula, and at the end of this video I'll provide some sources, provide a source that you can actually see how that was derived. So the best way to talk about this is through examples. And here's a question. What is the risk given that 600 beer bottles were randomly tested for a specific defect and zero defects were observed? So again, imagine, some supplier, let's say, and he's got a bunch of product on hold, but he's, sampled 600 of these beer bottles that may have a defect or, some kind of suspect nonconformance, and he found zero. Okay, does that mean there's actually zero defects in the rest of the sample or the bigger lot that he sampled? Well, here's where the 3 over n rule will tell us how bad quality could really be. So here we have n equals 600, so that's the sample that was tested. And we know that from our formula that the upper level risk is P equals 3 over 600. So basically taking this 600 and put it into this slot there. And 3 over 600 equals 0.005. So the actual failure level could be anywhere between 0 and 0.5% and still be consistent with zero observed defects in a sample of 600. And this is a 95% confidence limit. So again, it's saying that it's not necessarily saying it's going to be 0, but it could be as high as 0.5% and still be consistent with finding zero nonconformances in this sample size of 600. Okay, let's go to another example. Okay, we've got the same, let's say, bottle manufacturer, and he informs you that their process was generating cosmetic defects, and they think the defect proportion might be 1 in 5,000 bottles. So that's 0.02%. So you have a large number of suspect product on hold, and you're confident the defect is randomly mixed in the pallets. You need to find out if the hold has suspect non-conforming bottles in it. So what sample size do you need to assure that you will find one or more defects with a 95% confidence level? So here we're actually working backwards. So we know the p-value. Okay, there it's been estimated at 0.0002 or 0.02%. We don't know n, so that's what we want to estimate. So we know the rule, 3 over n, and we can rearrange these terms to get n by itself over there. So solving for n, we have n equals 3 over p, 3 over 0.0002, and that implies that 15,000 bottles would have to be randomly sampled and inspected to have a confidence, 95% confidence, of finding one or more defective bottles. So this, can also help determine, not just given a certain sample size, but it can also, provide a sample size determination given an estimated defect level type. So how would this play in? Let's try another example here. So following from the previous, you find out that the bottles in question are needed for a critical marketing promotion. It will be impossible to sample the 15,000 bottles and meet your deadline for time and cost. So you can only sample 500 bottles. What do you tell marketing? Well, you tell them that you can only randomly sample and inspect 500 bottles. And if you do this and you find nothing in that sample, then the 95% confidence interval for risk for the batch could be anywhere between 0 and 0.6%. So again, we take the 500 bottles, we put it in the 3 over n part, the n part right here, 3 over 500, and then you ask them if the risk is acceptable given the type of defect found and await their decision. So here's an example of how you would use this rule maybe to, allocate resources, optimize costs, or some kind of timing or something like that. And, I know a lot of times there's a criticism, statisticians will, sample sizes are never big enough. And, to get to those very small levels of, low risk, you have to sample such huge quantities of, let's say, product. But this actually, you can actually choose a level that optimizes some other factors, but at the same time, you have to let, whoever you're working with that, okay, I can sample this much, but here's your potential risk level. It could actually be 0, but it could be as high as 0.6%. And, if I find nothing, and that's kind of risk level I'm looking at. Now, if you do sample, let's say 500, and you do find defects, let's say you find 40 or 50, then the 3 over n rule really doesn't apply anymore, because now you've actually determined an actual proportion of non-conforming product, and that's going to be a different discussion altogether. So here's some useful tips on how to use this. The above assumes random sampling and independence between events. So you need to understand what random sampling is and is not. Okay. Sample sizes of 20 or more are recommended for the 3N principle to work properly. So if it's too small, it just kind of breaks down. And keep in mind that, this is a rule of thumb and just kind of a something to help you along. That statistics is evidence, it's not proof, okay? So when you're making a decision, this rule is just a piece of the bigger puzzle. So it's also about understanding the defect, let's say, how the product will be used and so forth. And the probabilities are also useful for comparative risk. Okay, so whether something actually fails or not is not usually known. So you may, sample your, 600 bottles or units or whatever and say, well, my risk could be anywhere between 0 and, let's say, 0.5%. And then, you always get asked the question, well, is 0.5% good enough? Well, it's relative to maybe some other percentage. Let's say, 0.5% versus, let's say, a 20% failure rate. So it's really about comparing risks rather than saying an absolute number is acceptable or not. The other thing to keep in mind is that probabilities don't guarantee whether something will fail or succeed. So, you can have very low risk and still have non-conforming product. So it's just a matter of really comparative risk than anything else. And remember that a confidence interval is like a fishnet. It's a statement related to the confidence of capturing the true proportion. One of the kind of misnomers in statistics is the idea of confidence, because people equate it with some kind of psychological, feeling or warm, fuzzy feeling. It's actually a statistical interval, whether or not you're going to capture the true, defect proportion under, let's say, repeated samplings. And, the key takeaway, and if you're not interested in really calculating this, or, you're getting, confused with the 3 over n and where to put the n and the p and all that, just keep in mind that just because someone claims 0 observed failures doesn't imply 0 risk. So really, you have to be a little bit skeptic here. If somebody comes up to you and said, listen, I've sampled something, I found 0 defects, don't assume that it really will be zero defects. Assume there may be some risk that certainly wasn't captured in the sample. Okay, so that's really what it's really all about. And if you want to understand a little bit more about this and how this rule was derived, really great resources, the Statistical Rules of Thumb, and definitely worth picking up a copy, and it kind of describes how that rule works as well. Okay, that's about it for today. Good luck, and we'll talk to you again.